Alright, hi there. So, I'm going to go over today now into chapter 9, and looking at section 9-2, where now in this chapter we're going to be essentially looking at two proportions or two means, depending on the section. So, I want to start with just a little bit of recap. So, in chapters 7 and 8, we introduced some of the actual methods of inferential statistics. And in chapter 7, we presented methods of constructing confidence interval estimates of population parameters. In chapter 8, we presented methods of testing claims made about population parameters. So that was the hypotheses test in chapter 8. And so now chapter 7 and 8 both involve methods for dealing with a sample from a single population, so just one number usually, or estimating one number. So now the objective of this chapter is to extend the methods for estimating values of the population parameters and methods for testing hypotheses to situations involving two sets of sample data instead of just one. So ultimately we'll work with like two means, two proportions, something like that instead. And so there's just a few examples on the next slide here of what some of those types of problems might sound like. And so it could be testing a claim to see what two weights may be, such as like with a freshman 15 problem. We could be testing the claim that a proportion of children who contract polio is less than children given a vaccine. So you're just testing two different populations. We could test the claim that subjects treated with Lipitor have a mean cholesterol level that's lower than mean cholesterol levels for people given a placebo. So ultimately, we're just testing two populations at a time. Alright, so now in this section, the key concepts are, we'll present methods for one, testing a claim made about two population proportions, and also constructing confidence interval estimates of the difference between two population proportions. So yeah, notice testing a claim made about two population proportions, and then testing the difference. That's what the confidence intervals will be for. Now this section is based on proportions, but we can use the same methods for dealing with probabilities or decimal equivalents of percentages because those are proportions still. Just depends on how you name it. So now, just real quick, some notation for that. Little lowercase p sub 1 will usually be the population proportion for the first data set, n sub 1, that sample size for the first data set, x sub 1 being the number of successes, p hat sub 1 being the actual proportion for the first data set, so taking that x1 divided by n sub 1, and q hat sub 1 still being 1 minus p sub 1. And we can use the same idea just with sub 2's for the second population. Now, something that we'll use in this section that's new is also called a pooled sample proportion, which is found a little differently. You find, so P, that pooled sample proportion, by taking both of the number of successes from the two populations, adding them up, and then dividing by the sum of the two sample sizes. Then, still similar idea, you use, to find Q bar, you just do 1 minus P bar. So notice a subtle difference, this is now P bar for the pooled sample proportion, rather than P hat. So some just requirements for these types of problems is we have proportions from two independent and simple random samples, and for each of the two samples the number of successes should be at least 5 and the number of failures should be at least 5. So hopefully similar stuff from before. Now, so the test statistics for two proportions is a little more involved here. This is what the null hypothesis will always look like, or something like this, for doing a hypothesis test of two proportions. Either proportion 1 equals proportion 2, or proportion 1 minus proportion 2 equals 0. So either way, saying that they're equal, or there's no difference between them. Now, how you find the test statistic is you take each of those sample proportions, subtract them, and you're subtracting out the claimed difference between the two, which will pretty much always be 0. And now you're dividing by the square root of, notice this is the pooled sample proportion, so p bar, not p hat, p bar, then the q bar divided by that first sample size, plus the same thing, p bar, q bar divided by the second sample size. Alright, and so for testing two proportions, we can use the p-value method, of course, which, since we'll be dealing with proportions, we can use table A-2, which is that z table. And you can also use the critical value method, which still uses table A-2. And then just based on our significance level, knowing how we can backtrack to find our critical values. Now, there is, of course, some technology that you can use for this as well. An applet I'd recommend in StatsMedic is a two-sample z-test for proportions. So real quick, just go through where to find that. Just kind of over with where the rest of our applets and tables are at. So just keep in mind again, z-tables here, because you'll need that later for this section. Just click on the applets there. And so you'll find just that applet, so two sample z-test for proportions under the traditional inference category. It's right there. Once you pull it up, it'll generate something like this. Okay, so now for an example, do people having different spending habits depending on the type of money that they have? So in a study, 89 undergraduates were randomly assigned to two groups and were given a choice of keeping money or buying governments. So now the claim is that money in large denominations is less likely to be spent relative to an equivalent amount in many smaller denominations. So let's see, this wording is a little strange here, but basically we're testing to see if the proportion of spending is different if, say, someone's given a dollar bill versus if they're given quarters. So I guess the quarters would be what would be used to buy the governments. So then we get both of those proportions from each of those. So number of successes with the dollar bill, 12, divided by that total sample size, 46. And then number of successes for the quarters, 27, divided by that total, 43. Those are two sample proportions. And now to get P bar, that pooled sample proportion, so we're doing the 12 plus 27, so both of the number of successes divided by the sum of both the sample sizes. All right, and just a little requirement check. So our 89 subjects were randomly assigned to two groups, and so we consider these independent random samples. Check, good there. Then these subjects given the $1 bill include 12 who spent it and 34 did not. And the subjects given the quarters include 27 who spent it and 16 who did not. So all of those counts are above 5, so then all of our requirements are met to do this example. So now just start doing a hypothesis test. So first step, just seeing what the claim is, that money in large denominations is less likely to be spent, and that's where you can express it mathematically, where P1 is spending for the dollar bills and P2 is spending for the coins. Now step 2 is just the opposite of that claim. So if this one is false, then that must mean that spending proportions for dollar bills is greater than or equal to spending proportion for coins. Then when you make the hypotheses, we'll see a similar theme here again where our null hypotheses should always involve equals in here somehow. So we have P1 equals P2. And then our alternative hypothesis being our claim this time that proportion for dollar bills spent is less than proportion for coins spent. All right, and we're going to test this at a 0.05 significance level. And so we're going to be using that normal distribution to run this test, or the z-table. Again, we've got our table of proportions, pooled proportion, our opposite of our pooled proportion, just doing the same 1 minus p bar there. Now, step 6, calculate our test statistic. Let's plug in all of that stuff into that formula there. So there's our p hat sub 1, p hat sub 2. Now, for our claimed values p1 minus p2, we're claiming that they're equal, so that difference is 0. That's why that's there. And then here's that p bar and q bar we got from the slides before, divided by each of those sample size, both added up and inside a square root. Once we evaluate all that, we should get a test statistic of negative 3.49. And so this is a left-tailed test. Now, we know it's a left-tailed test. One quick way to check is because the alternative hypothesis has a less than sign in it. That tells you it's the left-tailed test. If this were greater than, then it's a right-tailed test. If it's a does not equals, then it's a two-tailed test. All right, so essentially this one is a left-tailed test, so the p-value is the area to the left of the test statistic of negative 3.49, which comes out to 0.002, which when I look up in the z-table, Again, these are all left probabilities. So if I come down to the negative z-scores, and conveniently, actually, negative 3.49 is the smallest z-score on here, and I see that probability is 0.0002. So we're all good there. And in this case, since we're doing a left-tailed test with a significance level of 0.045, our critical value is negative 1.645, because to the left of negative 1.645, that area is 0.05, or that probability is 0.05. And because the p-value of 0.0002 is less than the significance level of alpha equals 0.05, reject the null hypothesis. So still consistent with what we've done with hypothesis tests so far. I'm just concluding there's sufficient evidence to support the claim that people with money in large denominations are less likely to spend relative to people with money in smaller denominations. And so it should be noted that the subjects were all undergraduates and care should be taken before generalizing the results to the general population. Okay, so there's all that. And now I'm going to show you how you can do that same thing on the applet. So you'd have to just type in all the information there and save some time. I typed it in right here. Now, so a trick that you have to do with the applet is you don't type in like the number of successes and then the total like we had in that first table. What you type in instead is so the successes and then the number of failures. So 12 and then 46 minus 12, so 34. And then for the other category for quarters, the 27 successes and then 43 minus 27, you had 16. You can click Begin Analysis. And you want to come down to the bottom under Perform Inference. Notice you're doing a 2-sample z-test, so all good there. Now you want to be careful of the alternative hypothesis because the applet organizes it a little differently. And notice, so we're testing the category spent, we're good there. Now back to the alternative hypothesis. So the way we set it up in our problem was P1 is less than P2. Now if I subtracted P2 from both sides, I would get P1 minus P2 is less than 0. So that's the option I want to select on the applet here. Then click Perform Inference. Gives me z-test statistic of negative 3.487, which when I round it up would round to negative 3.49. And that matches up with the test statistic that we had before. So just a little different when you use the applet. All right, then just finishing that off. So we can also construct a confidence interval to estimate the difference between the population proportions. Now, just a little caution. So the confidence interval uses standard deviations based on estimated values of the population proportions, and consequently a conclusion based on confidence interval might be different from a conclusion based on a hypothesis test. Now, basically, since the formulas for hypothesis tests of two proportions and confidence intervals of two proportions use different variables or parameters, then the hypothesis test and confidence intervals for the same problem of two proportions may not reach the same conclusion, just because they use different variables. So here's how you do the formula for the confidence interval of the difference of two proportions. You start with the difference of your sample proportions. Same idea as other confidence intervals. Subtract the margin of error to get the lower bound, add it to get the upper bound. And now this is how you find the margin of error for this kind of confidence interval. Take the same kind of z critical value and times the square root of now both sample proportions divided by, so the sample proportion, the opposite, then divided by the sample size for one sample. And then same idea just for now the other sample, so in this case the coins proportion times that opposite proportion divided by that sample size. And now you can use, again, another one of the applets for this, which when you look at just the list of applets, it's going to be this one right here, 2-sample z interval for proportions. All right, so for an example here, we're going to construct a 90% confidence interval to estimate the difference between those two population proportions and to see what other results suggest about our claim about people spending large denominations relative to spending small denominations. All right, and I'm going to finish that off in just a short second part of the videos.